Okay, section 6.5. This will be the last section that we do out of chapter 6, so the exam is not too far away. So we've seen inverse trig functions before in chapter 5, specifically section 5.4. This section is primarily going to be a review, but the new part that we haven't seen before is that we'll be looking at the graphs of the inverse trig functions. Okay, and again, we're only going to look at the starters here. We'll be looking at inverse for sine, cosine, and tangent, and probably not look at inverse secant, and definitely not look at inverse cosecant or cotangent. Okay, so looks like I need to get all the code going here. So we're going to look at the inverse of the sine function. So we start just by looking at the sine function. And remember, the sine function has a domain minus infinity to infinity and a range that is outputs between minus 1 and 1. Now, I've also drawn a horizontal line, this yellow line, onto the graph to point out that the sine function fails the horizontal line test badly. This horizontal line intersects the sine function in infinitely many places. And so sine x, as it's originally defined here, has no inverse. So what we do instead of looking at sine x, we look at sine x with a restricted domain. So we're only going to look at the portion of sine x that runs from minus pi over 2 to pi over 2. And the reason we choose this particular interval is because the sine function goes through all of its possible outputs, that is from minus 1 to 1 in this interval of x. Okay, and then again the yellow line showing us now that on this restricted domain, the sine function does pass the horizontal line test and therefore will have an inverse. Okay, so I don't know of any notation for the restricted sine function, so I just had to put in the words. We restrict the sine function to minus pi over 2 to pi over 2. This will be its new domain, and this will be the range or the output. Okay, so this restricted sine function, again restricting to this domain, will have an inverse, and this is how the inverse is defined. So again, we've seen the symbols before. Sine to the minus 1 here is the symbol for the inverse sine function, and it's defined in symbols this way. Y is the inverse sine of x if x equals sine y. I usually think of it in words. Y, the inverse sine of x, is the number in this specific interval here whose sine is x. Okay, so if you remember, the range and domain for a function and its inverse swap around. So this restricted sine function had a domain, the inputs, minus pi over 2 to pi over 2. And that says that the inverse sine is going to have that interval as its range. Right? So it's very important to keep track of this. The inverse sine function, it's going to take numbers between minus 1 and 1 and return numbers, that is output numbers, between minus pi over 2 and pi over 2. Okay, the alternate notation here is the inverse sine is sometimes also called the arc sine function. And you'll see me type that in the Mathematica commands. Okay, so like I said, here's the new thing. We had not looked at this graph before, so just walk through the process one more time. We start with looking at the sine function. Infinite domain goes on forever, but then we restrict it. This is the blue graph where we are only going to look at the sine from minus pi over 2 to pi over 2, and then we'll put in the graph of the inverse sine now. And just a reminder that this graph is going to be the reflection across the line y equal x, the reflection of sine x. Okay, so this is the red graph here is the graph of inverse sine. And one easy misconception here is that the lines x equal minus 1, this vertical line, and the x equal 1, these are not vertical asymptotes for the graph of inverse sine. Inverse sine actually starts right here at this red dot. It starts at -1, negative pi over 2, and it seems to almost look exactly like y equal x for a little while, and then it's going to pop up here and end exactly at 1 comma pi over 2. Okay, not vertical asymptotes. Very important to catch that. Okay, so we'll go through cosine and tangent in the same way. Again, I guess I could hide that. I can do that later. Cosine, as it initially stands, does not have an inverse because it's, again, horribly, badly failing the horizontal line test. So once again, we're going to restrict the domain of this function to some interval that does pass the horizontal line test. And the interval that we choose now is going to be from 0 to pi. Why do we choose this interval? Well, it is an interval where the cosine is taking on all of its possible values. When x is 0, the cosine starts at 1, and the cosine makes it down to -1, its smallest possible value, when the x gets up to pi. Again, the yellow line just indicating that, oh, now we are passing the horizontal line test, so we should have an inverse for this function. Okay, so same idea here. We're restricting down the cosine domain to a specific interval 0 to pi. Okay, so the inverse of cosine then, denoted cosine of the -1, is the inverse of the cosine function, but on this restricted domain, just from 0 to pi. Again, in symbols or in words, I'll focus on the words, inverse cosine x is the number in the specified interval whose cosine equals x. Okay, so again, we see the switch around here. When we're looking at the cosine function on its restricted domain, it's from 0 to pi. Those are the inputs. Consequently, those are going to be the outputs, the range of the inverse cosine, also called the arc cosine. Okay, so let's look at the graph then. Again, we'll walk through the 3 steps. Start with the full cosine function, and then pare down the domain to an interval where we're passing the horizontal line test. And then to get the graph of the inverse, now we're going to reflect across the y equal x line. So this will be a little abrupt here. And it looks quite different. So the red graph now here, this is the inverse cosine. We see it is, I think, an accurate reflection across the line y equal x. Okay. Once again, these vertical lines at x equal -1 and x equal +1, these are not vertical asymptotes. Moving from left to right, the graph of inverse cosine starts out at -1 pi and ends here over on the right at 1, 0. Okay, one more to go of the starters here. We'll look at tangent, and actually I have slightly different graphics here, but so remember the tangent function. This repeats every pi. It has period pi. It has these vertical asymptotes at every odd multiple of pi over 2. But the yellow line, once again, is telling us this tangent does not have an inverse because the horizontal line is intersecting in more than one spot. So once again, we're going to try to restrict the domain so that we do pass the horizontal line test. And this time we're going to choose the interval from -pi/2 to pi/2. Okay, so we are now passing the horizontal line test, so the restricted tangent function will have an inverse. And here's its definition. Right. So the domain we restricted from -pi/2 to pi/2, but this is an open interval now. Okay, so because the tangent function is not defined at -pi/2 or pi/2. Okay, so the inverse tangent is the number in the specified interval whose tangent equals x. We'll do some computation soon. Okay, so again, the switch around here, the important thing to keep in mind here is that the inverse tangent is always going to be some number in the interval from minus pi over 2 to pi over 2, also called the arctan. Okay, and then lastly, I'm not doing this as an animation, I'm just showing the blue graph. This is the tangent plotted again just from minus pi over 2 to pi over 2. And when we reflect across the y equal x line now, we get the graph of the inverse tangent, this yellow graph here. And I guess I should point this out. The lines y equal minus pi over 2, these horizontal lines, and y equal pi over 2 are horizontal asymptotes for y equal, shoot. I have this feeling like I really had it that time. I think I have a, I just missed the y, asymptotes. Okay. All right, so where are we? 11 minutes. So we're going to evaluate the inverse trig functions now on specific numerical values. Again, something we've done before, but when you do these, the key point to remember always is the range for these functions, what the outputs are supposed to be. So when you're computing inverse sine, you got to remember that your answer has to be in this interval from minus pi over 2 to pi over 2. For inverse cosine, the answer has to come between 0 and pi, and inverse tangent here as well. So key thing to remember. Okay, so what we're going to do here, and I don't think our book has problems like this, but on the quiz or the exam, it's going to be stated this way. Evaluate these if they are defined. Okay, so find the inverse sine of a half. Okay, so this is supposed to be a number whose sine is equal to 1/2. So this suggests that we try to solve this equation, find the x whose sine is a half, and we have to make sure that we choose the x in this interval. This is the interval where we make our choice. That's going to be the output of sine, the inverse sine function. Okay, so can we think of any number whose sine is a half? Yes, I believe pi over 6 works. And pi over 6 is in this interval. It's between minus pi over 2 and pi over 2. Just to point out here, there's another x that would work here. Another x would be 5 pi over 6, but 5 pi over 6 is not in this interval. Maybe I'll go ahead and maybe include that in the PDF. Both x equal pi over 6 and x equal 5 pi over 6 solve the equation, but only pi over 6 is in the required range. Okay, let's find inverse cosine of -1/2. So again, we're looking for a number whose cosine is -1/2, and we want to make sure that the x that we choose, if we happen to think of more than one, we have to make sure the one that we offer up is in the interval from 0 to pi. Okay, so let's see, I think if we need to go past pi over 2 so that our terminal point comes out to be in the second quadrant. And this should be a small x value, so I think we want this steep. So I think this is 2 pi over 3. There are other x values whose cosine is equal to -1/2, but this is the only one that falls in the required interval from 0 to pi. Okay, let's try another one. We're going to find the inverse sine of square root 3. Okay, so that means we're looking for a number whose sine is square root 3. And we'd want to make sure that we chose our number x to be in. I'll go ahead and complete this part of it. But hopefully you're balking at this, because there is no x whose sign is square root 3. Sign is always a number between -1 and 1. And square root 3, I don't know what it is as a decimal. It's bigger than 1. That's for sure. So there is no solution. So this is not defined. So if they are defined, and here you can just write DNE, this one does not exist or is not defined. Right? This is another way of saying that, another way to explain why this is not defined is simply to say that the square root of 3 is not in the domain for inverse sine. The numbers you plug in, the inputs to inverse sine, have to be between -1 and 1. That's why this one is not defined. Okay, one more. So we just looked at this inverse sine. So, oh, the number needed to be between -1 and 1. This is not true for tangent. This one actually is defined, even though the number we're plugging in is bigger than 1. And this one is maybe the hardest to mentally remember here. We're trying to find an x whose tangent is square root 3, and we're going to make sure that we choose the x in this interval. Again, this is just a convention that we agree upon. It has to be in that interval. Okay, so the way I tend to think about this is in terms of angles. Tangent is y over x. This root 3 is bigger than 1. That means I want my y coordinate to be the bigger number. I want y bigger than x. Now, however you think about this, it's okay. But the angle where the y is bigger than x is the steep angle. So pi over 3 is the answer here. And pi over 3 is in the interval between -pi over 2 and pi over 2. How are we doing? We're about at 18 here. Okay, so we're going to look at the cancellation properties of trig functions and their inverses. And I've got 2 rules for you to try to internalize, maybe put on a note card. If you're looking at a trig inverse, that's going to equal x. I'm sorry, trig inverse x will equal x. We'll get cancellation. But this is only going to happen if x is in the domain of the inverse function, this inside one. Okay, so that's where we'll look at 3 examples here. All of these are trig of inverse trig. And what I want you to do is, and on the quiz or exam, I'll be asking you something like this. Simply mark these statements as being true or false. And you really want to make sure you know this rule, because if you're relying on your calculator to check each one of these, like I might purposely put in a dozen of them just so that using your calculator becomes almost infeasible. You might not have enough time. So make sure you know the rules. Okay, so this will be equal as long as the x number is in the domain of sine inverse. Right? So again, just try to remember the domain for sine inverse sine is -1 to 1. So that's why this one is true. Right, so what's the domain for the inverse sine function? Well, this is the surprising one. This domain goes from -infinity to infinity. So this one is going to be true, and maybe something to add is that this one involving tan, inverse tan, this one will always be true, at least for real numbers. It doesn't matter what number you plug in there, because the domain for inverse tangent is all real numbers. All right, so let's check this one out. What's the domain for cosine? Oh shoot, I don't have any that have failed here. I beg your pardon. The domain for inverse cosine, I almost fooled myself, is -1 to 1. Okay, so that's an especially tricky problem, I think, because that pi might get you thinking about the range for the inverse cosine, but we have to look to the domain of inverse cosine. So this one is false. False. And the underlying reason here is this is undefined. Maybe I can make a sentence out of this. That's domain. Not really a sentence. Okay, so that's the one variation, trig, inverse trig, and then we'll put them in the other order and look at a few examples there. So again, I've tried to make this general rule for you here. You'll get equality with this identity, but this time it's only when the x is in the range of the inverse trig function. Okay, so the thought here is that we've decided what the output for the inverse function should be. So if this number x isn't in the range for the output function, the answer can't possibly be right. All right, so this time again we're looking at the range. Oops. Range of sine inverse x. All right, so these are the outputs. We've agreed that we'll always output numbers from minus pi over 2 to pi over 2. And so this one is false. Because pi is not in that range. This is a little like a quiz problem I think I asked, or maybe it was a practice exam. Is that even when your partner's handwriting was so bad you couldn't read what was inside here, you'd know that this answer has to be wrong because it's not in the correct range for the function. Okay. Range for inverse tan is, it's a small detail, but I would like you to get it right. This is the open interval. So this one is false as well. This is range for inverse cosine. So this is 0 to pi. Oops. This one is true since pi over 6 is in the range. Okay. We're going to look at doing some evaluations where we don't get cancellation now. And the reason we don't get cancellation is maybe because one of the two rules is broken, or maybe because the trig functions don't match. Okay, so for a problem like this, sine inverse cosine, what you really want to do is, there's more than one way to do it, but probably the most systematic way is simply to evaluate the inside function first, if possible. So maybe I'll try to break that down into two steps. One, evaluate cosine minus 1. The inverse cosine, let's not call it cosine minus 1. And we do that by trying to solve cosine x equal minus 1/2. So we need to find a number whose cosine is minus 1/2. And but I believe that's exactly the problem that I did up above. This is 2 pi over 3. Okay. just as a constant reminder here, that is in the correct interval. That's in the range. Okay, so now what we have is, I think this is in the notes up above as well, but I just want to make it crystal clear if I can. We've evaluated what the inside of this composition is, and no, I'm probably making it too long. I'll go shorter on the next one. All right, plugging that in. And now we want to get the sine of 2 pi over 3. Okay, so we're in the second quadrant. It is a steep angle. We want the y coordinate, so I believe this is root 3 over 2. Okay. Again, so I do this just a little bit faster. The inverse tangent of 1, we're looking for a number whose tangent is 1, and pi over 4 is such a number, and it's in the correct interval. It's between minus pi over 2 and pi over 2. And so now we just take the cosine of that inside number. Okay. Strangely, in this section, the only problems that the text is asking you, and I think I'll do this on the exam too, are problems where the inside inverse trig function is a value you can compute without a calculator. Back in chapter 5, to do this problem, we would have used a triangle approach. We would have drawn a triangle where an angle was equal, where an angle had a sine equal to 3/5. But we're going to skip both of these for this chapter because our text is skipping those. Okay. Almost lastly here, we're going to switch this around and look at some inverse trig of trig functions. Okay, so the first thing to think about here possibly is like, oh, this is the same. It's an inverse sine and a sine. So maybe I get cancellation. But you don't. You don't get cancellation. Maybe I'll put this in. Is false. Since pi is not in the range for inverse sine. Oops, I missed my minus sign. So we need to evaluate one step at a time, just like we did up above. So the inside function, the sine of pi, go ahead and do it first. That's a y coordinate of 0. So we're at the far left. We have number pi, that would be terminal point, -1, 0. We want the y coordinate, and that's 0. Okay, so now we're going to compute the inverse sine of 0. We're looking for a terminal point that has y coordinate 0, and that's coming out with a number 0. Right? And this is correct since 0 is in the range, the agreed upon range for the inverse sine. Try one more. So this one, cancellation is not possible because the two trig functions are different. So again, we just do the layers one at a time. The cosine for pi over 6, the reference point for pi over 6 is root 3 over 2, comma half. Cosine, we want the x coordinate, so this would be root 3 over 2. Okay, so right. Now we're looking up. Yeah, I had to push pause there just for a second. I'm thinking I was blanking on something, but we can't do this. So I'll just cut this out of the PDF as well. Sorry to put you through it from the video here. Okay, so we'll try one more here. The question might be, don't we get cancellation here? Isn't this just negative pi over 3? And the answer is no. And because negative pi over 3 is not in the correct interval. Inverse cosine is always supposed to give us an answer between 0 and pi, so this one is false. Right, so because of that, again, we need to evaluate one stage at a time. Let's see. Negative pi over 3, that's down in quadrant 4. The x-coordinates are positive there, so this should be square root 3 over 2. And now we're trying to find an angle whose cosine is square root of 3 over 2. Oh, beg your pardon here. Did I get that right? No. This should have been 1/2. This is a steep angle, so the x-coordinate should be small. Boy. See if I can get out of this. And now we're looking for a number whose cosine is 1/2, and one that we choose, because it's in the correct interval, is the pi over 6. My goodness, pi over 3 number. All right, hopefully that's correct. I only have one last thing to say here, so I won't timestamp here. Just a reminder, and we talked about this back in 5.4 as well, this notation. When we write the Pythagorean theorem and we write sine squared and cosine squared, the location of this 2, it's just a convenience, I guess. What it's representing is this quantity sine of x squared. But the notation for the inverse sine is something quite different. So I just re-emphasize that the inverse sine function does not mean sine of x raised to the -1 power.